All right. Good morning. It's 10:25, so let's get started. Happy Monday, last Monday before finals. Crazy. Thank you for being here. I put a couple of things up on the announcement for today for Canvas, so hopefully you had a chance to check that out before right now. One of them is a copy of this, the unit circle. And we'll get into that a little bit today as a recap from what you might have seen last year or the year before. And the second thing is the solutions to the homework that was due on Friday, homework 4.1, which went through degrees to radians, radians to degrees, and a little bit of the arc length, radius, theta relationship, just solving for either one. A couple of things that I saw as I was looking through some of your work for that last night. Mistakes that I saw that were more common than others. Number one, making sure you show every little, at least preliminary steps of work to get you from one to the other. I don't want just a list of answers. Right? That doesn't do me any good into getting into your head and seeing if you really understand this stuff. At least give me a formula that you started with and then the substitution, and then you can simplify from there. I don't need to see every single step, but I do want to see some work so that you know where this stuff comes from, how it works. That came up a little bit, not a ton, but some people just need to show a little bit more work. And if you need to do that and you want your grade to go up because I dropped you a little bit because it was very barren of work, then do that and just tell me that you've resubmitted it, and I'm happy to change your grade. But number two, I saw a lot of people just kind of blindly go through the motions with 89 through 100, where the angles were given in degrees and you didn't change it first to radians. Okay, that was the only other thing that I saw. Like people were saying, I don't know, I forget what it was, but like, in a circle with a radius of 8 inches, and we go around 330 degrees, some people said that the measure of that arc was like 0.024 inches. If that length is 8, there's no way then that you know what I mean? That's a quarter of, no. So the numbers themselves have to make sense when you write them down. Don't just write down what the calculator says, make sure it makes sense to you, right? You would have had to change 330 degrees into radians first, right? And anything that's in degrees, change it to radians, right? Expect that most of what we're going to do will be kind of required units with radians, because everything works with radians, right? The theta equals S over R only works with radians. And all the 4 different forms of that calculus. We're really going to focus a lot on radians once we get there, with a little bit of trig that we do. Now, so that was that. Okay, a couple things just from that homework that go back and fix them, right? The reason why I'm focusing on the things that I'm going to focus on here for the, let's say, 6 weeks or so at the most, that we'll do with trig kind of leading up to calc. I'm looking directly at this fall's college trig final from CU. And kind of picking out the things that they thought were most important and focusing on those, okay? There's so much more that I love about trig that I won't get to, and that's okay. I wish we had a whole semester elective dedicated to trig so I could do all sorts of fun stuff. But this is what we've got, so that's what we're gonna go with. And what I wanted to do first was work on this, okay? Looking at a circle that has a radius of 1 centered at the origin. Okay. Now I included a copy of this on Canvas, and it's just a PDF of a blank unit circle. Unit circle, radius of 1 centered at the origin. Okay. Now I could pick any circle I want. I could put it anywhere, and I could make it as big or as small as I wanted. But this makes all of the coordinates work out a little bit nicer once we get to the outer parts of this circle. You can see there's kind of like 3 layers to this, right? There's an inside part with all the degree measures. There's another part that's inside the circle that doesn't have any units written there. Those will be our spots for radians. And then the coordinates will go along the outside right there. And I'll try to do my best to talk this out. I know that it's kind of far away, but I wanted you to see the whole thing as we go. And although this is mostly stuff that you've probably seen before, maybe it's not, or maybe you just don't remember. And I want it to hopefully make more sense for you as we go, okay? So I'm gonna work my way from the inside out. But the first thing I'm gonna do is mark off some of these nice coordinates along the way, the ones that are really easy, because they land on an axis, right? Imagine, so that's the x-axis, this one's the y. So I'm gonna pick these 4 spots first and just kind of write down each of those coordinates, knowing that the radius is just 1. I'm just gonna go 1 to the right, 1 up, 1 to the left, and 1 down, right? So there's 1 to the right, 1, 0. Going up from the origin would take me to 0, 1. Going 1 left from the origin would be -1, 0. And going straight down from the origin would be 0, -1. Okay? And let's fill in the degree measures. First, we'll do degrees, then we'll go to radians, okay? That go with those, okay? Remember, standard position for all these angles means we're gonna start on the positive x-axis and we're gonna open them up from there, okay? I could go negative and I could go this way and it would all still work, but it's much easier if we think about positive direction for angles as often as we can. And if I haven't opened an angle yet, that angle measure is 0, right? 0 degrees. And although I would say I can't draw myself a nice right triangle when I do that, I still want to, before we get to triangles, we're going to do all this stuff before we get to triangles, except for the outside. Then we'll go over to the board and I'll talk a little bit about triangles so we can figure out some things. But imagine, I'm just starting right here and I've got 2 sides, right? I've got an initial side and I've got a terminal side, and let's just start opening up some angles and see what happens, okay? So let's go up to the top and we've got like that nice right angle right there. Anything I draw here, like on the very inside, don't draw that. It'll get too complicated because I'm just gonna keep erasing stuff. But all of these blanks, we'll fill all those in. Okay, well, that's a 90-degree angle. Okay. If you don't have a copy of this printed out, that's okay. You can draw it yourself, or you can come back to this video later and fill that stuff in. Okay. Okay, so open up another 90 degrees, right? Get us all the way around this circle to the other side, not all the way around, but get us halfway around the circle itself. That's a straight angle. Straight angles are 180. Right, so you opened up this full angle right there to get to there. Okay, if we kept going all the way around to there, and you can see I keep starting at the beginning, right? There was 90, there's 180, there's another 90 after that, so that's 270 degrees. Pick the blank spot that has a degree symbol. The other ones will be for radians because there's no units there, and we don't need units when we're talking about radians. And then let's make all the way around. Let's go all the way back. 1 full trip around the circle. That's why there's another spot at that same terminal side, right, for 360. Right? And those are the spots that end up at really, really, really nice locations. Okay. And real quick, I'm just going to take you over here just for a hot second, okay? Because I don't know if you've heard this before. It might be a little shaky because I'm holding it, but angles that end on an axis somewhere. Okay? That if you open up an angle and you end up not in a quadrant, right? Because here's quadrant 1 and 2 and 3 and 4, but those are the insides, right? If you end up on an axis somewhere, you're not inside a quadrant, you're between them, okay? They have a name for those. They're called quadrantal angles, okay? Q-U-A-D, quad. R-A-N-T-A-L, quadrantal. There's my symbol for angles, right? I keep using that angle. Okay? Those are called quadrantal angles. Angles that end on an axis somewhere. Doesn't matter which one. Doesn't matter what direction we went to get there, whether positive or negative. But one that ends up on an axis, that's going to be a quadrantal angle. So when you hear me say that, now you know what I'm talking about. When we get to that, probably like tomorrow, we'll start talking more about that. Okay, cool. So that's that. Now, I'm gonna get rid of some of this inside stuff because we're gonna open up a whole bunch of different angles, okay? What I wanna do is I wanna fill in all the rest of the degrees first. And the easiest way to do that is to pick, and this is what the unit circle does. It picked really nice degree measures from really nice spots along, like, because remember what we're doing. We're just gonna track this dot. Right? We're gonna track the movement of a point along the circle. I said it before, I'm gonna say it so many times that you're probably gonna get sick of me saying it, but we're not stuck anymore, right? Everything that we're gonna do, we wanna think about things happening in motion. So what I wanted to do, and what trig allows us to do, is stop at really nice spots along the way, and all those spots you're gonna see are gonna be multiples of 30 degrees and multiples of 45 degrees, and those are our first two spots, okay? Again, like there's 30, there's 45 to get you to there, okay? Starting at that standard position and kind of opening up from there. And so what you can see is that like this tiny little wedge in here, and really all of these tiny wedges in here, those will all be 15 degrees more than where you got, right? 30 to 45 is a difference of 15. The big wedges will all be 30s, okay? But because we're just gonna go like 30, 30, 15, 15, 30, 30, 15, 15, 30, 30, 15, 15, 30, all the way around, just like that, you're gonna see that everything in here is gonna be a multiple of 30 or a multiple of 45, and sometimes both, okay? And so let's do that, okay? 30, another 15 is 45, another 15 is 60. Another 30 gets us to 90, good, we did something right so far. Another 30 after that is 120. Again, stay on the inside. Make sure that you're filling in the spot that has the degree symbol next to it. 15 more than that is 135. I know it's a little small to see, hopefully. You can always zoom in right on if you're on your computer or on your laptop or tablet or phone, or even, so you can see these numbers a little bit better. 15 more than that's 150. 30 more than that's 180, which is good. We got ourselves to a good spot there. 30 more than that is 210, so that's like all the way around 210 degrees. 15 more, so 225. 15 more, 240. 30 more, 270. 30 after that, 300. 315. 330. And then back to 360. Okay. Centered at the origin, radius of 1. This works out really nice. Now, centered at the origin, radius of anything else, these degree measures are still true. Centered anywhere you want, radius of whatever. Right? You can build a circle. Degrees don't seem to care too much about that. Okay. Now, proportionality of trig is what saves us from all this trouble. When we talk about radians, we talk about locations on the circle. It's pretty specific to the unit circle, but because of proportions, it still works. And I'll show you that once we get back over there and we talk about trig proportions, okay? Let's do some radian conversions here. I'm just gonna switch colors. I'm gonna go blue so that they stick out a little bit. And let's just convert them all. Now that could take forever, like multiplying everything by pi over 180 and then simplifying. And then making sure you really stick with the pi, and you could do it that way, you really could, and that's fine. If you know your degrees, you can figure out your radians by converting, or vice versa, okay? I'm gonna make this hopefully a little bit easier to recreate so that you're not kind of like brute forcing all of these, and that you can start not, like I'm an understander, not a memorizer when it comes to this kind of stuff, and trust me, that's gonna serve you really well when it comes to trig, understanding how to create this, not memorizing how to recreate it. That makes sense? So that's what I'm gonna do. I'm going to use understanding of the fact that the circumference of this circle, 2 pi r, specific to this one, the blue and the black, I don't know if you can see that well. Let's go green. That's purple, I like purple too. The circumference of this this circle is gonna be 2 pi. Okay, again, you don't have to write any of this stuff over here. This is like the middle, and over here, this is kind of where I'm gonna write some stuff down, okay? Here we go. I don't go anywhere, I've gone 0 radians. I go all the way, I've gone 2 pi. Okay, so that blank spot right there, put a 0 on top for having like gone nowhere just yet, and the 2 pi underneath for having made it all the way around. And what I want to do is start chopping up that journey that we just took all the way around in half, and then in half, and then in half, as far in half as we can go. Okay, so let's go just halfway around the circle instead of all the way. Well, all the way was 2 pi. Let's cut that in half. Half of 2 pi, 2 divided by 2 is just 1. Okay, so pi, right? And we know that pi and 180, pi radians at 180 degrees are the same. That's what we use in our radian to degree to radian conversion that we did, which was really nice from Thursday or Wednesday or whenever it was. Thursday, right? Friday? I don't know. Okay, cool. Let's chop it in half again, okay? Half of 180 is 90. And so I should be able to do the same thing to pi. I should be able to just cut it in half. But the problem with cutting an irrational number in half is it's still irrational. And there's no really nice way to write pi over 2 other than just pi over 2, right? Now, so what I'm going to start doing here, because these 3 numbers are the only ones that aren't fractions when it comes to radians. Everything else from here, I'm going to start chopping pi into pieces and then taking multiples of those. So we're going to have these fractions. And so these bars right here, these empty spaces are no longer just a blank spot. To me, they are now the fraction bar of each of those radian measures, where I'm going to put the numerator on top and the denominator on the bottom. So when I write pi over 2 in that tiny little space, I'm not going to squeeze pi over 2 above the line. I'm going to put the pi here and the 2 down there. Now, what that means is that every 90 degrees is another pi over 2. And that as I take a trip around, thank you, Riley, as I take a trip around the circle, every 90 degrees, I should be going an additional pi over 2. Okay, cool. 0 pi over 2 starts right here. Awesome, 0, right? 1 pi over 2 is right there. 2 pi over 2 should be right there, and the 2's cancel. Yeah, I got the pi. Okay, so 1 pi over 2, 2 pi over 2, another 90 degrees. 1 pi over 2, 2 pi over 2, 3 pi over 2. And I'm going to write the 3 pi on top and the 2 on the bottom. So this is kind of one big fraction. So like that bar would extend out just a little bit for me, since like it's pretty small for me to write on this. And then I'll go another pi over 2. Okay, 2 pi over 2, 3 pi over 2, 4 pi over 2, yay, 2 pi, and we're good. So we made our trip around the circle, and we should be able to judge our markings if we do it right. We should end up at like these really nice spots along the way as we go. And these are as simple as those can get. Okay, so all of your quadrantal angles are multiples of pi over 2. Okay, cool. So here we are at 90 degrees. Here we are at pi over 2. Let's cut it in half again. Because if I do that, if I divide the fraction of the decimals and the fraction of the radians, they should just divide nicely, okay? So cut 90 in half, it gets me to 45 degrees, which is good because I'm looking for multiples of 45 around the circle. Well, if I cut 90 in half, I better do the same thing to pi over 2. And if I'm making a fraction half as big, pi over 2 times 1/2, what should happen is the denominator should get twice as big, right? Cut things in half, make the denominator, yeah, 2 times 2 is 4, perfect. Okay, nice, that worked out. Again, I'm just gonna use this middle space to kind of jot stuff down that I just want you to hear and see, but mostly just hear from me. Every 45 degrees is pi over 4 radians, which means like this length, you don't have to draw this, but that length right there, that curved arc, has a measured length of pi over 4. Exactly pi over 4, which is cool. And that's what radians does, right? It helps us measure that outside. But it's also what's going to be like what we use to measure the angle as well, so that it works out super nicely for both. Okay, cool. So what we've got now is that every 45 degrees is another pi over 4, and all I have to do is count my pi over 4s all the way around. 0 pi over 4, 1 pi over 4, 2 pi over 4, 3 pi over 4, 4 pi over 4, all the way around. Hopefully we can kind of convince ourselves we're doing it right when we get to those quadrantal spots, and oh yeah, that simplifies perfectly, right? 0 pi over 4, love it. 1 pi over 4, great. 2 pi over 4, yeah, pi over 2, right? 2 and 4 is 1/2, perfect. Okay, 1 pi over 4, 2 pi over 4, another 45 degrees, 3 pi over 4 at 135. 1 pi over 4, 2 pi over 4, 3 pi over 4, nice, 4 pi over 4, the 4's cancel, another 45 degrees to here, 225, 5 pi over 4. And you can't simplify that, so we're good. Okay, 4 pi over 4, 5 pi over 4, 6 pi over 4, nice, 3 pi over 2, that one works. Okay, another 45 degrees, 7 pi over 4. And then 45 more gets you back to the beginning, 8 pi over 4, nice, there's 2 pi. Okay, and what you'll see is that any of the multiples of 45 that don't end at a quadrantal spot have that 4 underneath, right? Multiples of 45 have a 4 in the denominator, and they all end in a 5. 45, 135, 225, 315. That's the only angles on this circle that have a 5 as their last number. Okay. There are so many relationships in this thing, it blows my mind. Okay, cool. There's all your multiples of 45, good, all right? Now for multiples of 30. Well, how are we gonna get to that? I can't cut 45 in half anymore. That's 22 and a half. And yeah, that's an angle, like 22 and a half is like right there somewhere, okay? That is, okay, pi over 4 cut in half, yeah, pi over 8, sure, okay? The problem is with the location of the point at the end here. There is no really nice way to write that number down other than some string of irrationals, okay? Every spot along this circle has numbers that work, right? We can find those locations. But what we're going to try to stick to with the unit circle are the locations that have nice degree measures, nice radian measures, you know, multiples of pi over 4 and then for 30, but also have relatively nice coordinates as well. Okay, all this stuff exists, you know, 1 degrees, 2 degrees, 3 degrees, 0.5 degrees, pi over 97 radians, whatever. All of those have spots, but they're just not nice. So we're going to stick with the nice ones. It's going to get messy enough anyway. Okay, cool. So how do we do that? Well, let's see. I don't know what you can see. Let me go like with green. Where does this green work? Let's go like bright green. Does that contrast well? Yeah, there we go. If I want to turn 90 degrees, I want to like do something to turn it into 30 degrees. I want to divide by something, right? I want to divide by, well, 90 divided by something is 30. 90 divided by 3, right? Well, that must be the same thing that I'm supposed to do to pi over 2 to change those radians. And of course, I could do 30 times pi over 180 and get all this done. But just so that you can see how to create it on your own, right? Dividing by 3 is the same thing as multiplying by 1/3. This and this are the same thing, right? And so multiply across pi over 1, pi times 1 is pi, 2 times 3 is 6. And I think you did that one on the homework. I think 30 degrees was one of the conversions that we did. 30 degrees is pi over 6 radians. And you could have done that by changing 180 into 30 by dividing by 6. Okay, take pi and divide by 6 and you get there too. What that means now is that every multiple of 30 is another pi over 6. And if you want to count your way around that way, we should be able to do it. And we just simplify along the way. And what you'll see is that once we get to 60s, any multiple of 60, 60, 120, 180, 240, 300, and 360, all of those will be simplifiable because you'll have an even number of 30s. You'll have 2 30s, or 4 30s, or 6 30s, and you'll keep going around, okay? So here we go. 0 pi over 6, yay, 0. 1 pi over 6, okay, pi over 6. Another 30 degrees, so skip the 45. Okay, we're not gonna land on that one. 30 more degrees, okay, that should be 1 pi over 6, 2 pi over 6, right? And if you've got a number like 2 pi over 6, the pi is still gonna be there, but you can simplify the fraction to be 1 over 3, right? So we get this pi over 3. And what that tells me is that every 30 degrees is pi over 6. And every 60 degrees is pi over 3. 6 and 3, 3 and 6, they go with each other. And you're going to see there are going to be a lot of going with. There's going to be a lot of connections that we're going to make between the 30s and 60s. Okay, so you can either go all the way around with your 30s, or you can go all the way around with your 60s and fill this thing out. Let's go around with the 60s because those will already be then simplified, which is really nice. Every 60 degrees is pi over 3. Okay, 0 pi over 3, 1 pi over 3, it's 60. Okay, let's go another 60 to 120. 0 pi over 3, 1 pi over 3, 2 pi over 3. Another 60 degrees from there is pi, okay, right? Because 180, 3 pi over 3, 1 pi over 3, 2 pi over 3, 3 pi over 3, yay, we did it again. Okay, another 60, so skipping down to 240. 1 pi over 3, 2 pi over 3, 3 pi over 3, 4 pi over 3. Just counting pi over 3 sections, that's all we're doing, right? Okay, so 3 pi over 3 at 180, another 64 pi over 3 at 240, another 60, so 2 big wedges, okay? 5 pi over 3. And then one more 60 should get you to 6 pi over 3. There's 2 pi. And the only blank spots that we have left are multiples of 30 that just aren't multiples of anything else, okay? But I can count my way around by 30s by counting pi over 6s. 0 pi over 6, 1 pi over 6, another 30, 2 pi over 6, 3 pi over 6, 4 pi over 6, 2 pi over 3. Okay, here's a blank spot finally. 3 pi over 6, 4 pi over 6, here we go. 5 pi over 6. At 150, 5 pi over 6. And then 180 is 6 pi over 6. The 6's cancel, yay, we're good. Here's a blank spot, 7 pi over 6. Another 30, 8 pi over 6 is 4 pi over 3. 9 pi over 6 is 3 pi over 2. All those are all filled in. 10 pi over 6 is 5 pi over 3. Those are all done. The only one we haven't done, let's see, 9 pi over 6, 10 pi over 6, 11 pi over 6. And then one more gets you back to 2 pi because that's 12 pi over 6. And as messy as this looks, and it really is, there's a lot of beauty in how perfect these things all work out. And like I said, there's a lot of angles that are missing, of course. I mean, there's a ton of stuff that we could fill in between for like nice angle measures, nice coordinates, we'll get to coordinates in a second, or nice radian measures, but not all three at the same time. And we're gonna count all of these as all being relatively nice compared to the rest, okay? Now, as we work from the inside out, the last thing we have to fill in are the coordinates in between, okay? But first, any questions? It's gonna be a lot of me talking today, sorry. And hopefully it's stuff you've seen before. I just kind of want to recap, refresh, reinvigorate. Good, okay. Come with me. Back over here. Okay, to help us figure out the coordinates that go with all of those points, all of those degree measures and radian measures, what we're going to need is to figure out where all this stuff comes from. Okay, so imagine, now you don't have to write this down necessarily, but imagine you want to write some of these things down so you know where it comes from. Right, here we are drawing ourselves a little graph. And we start over here at 1, 0. Right? We've got ourselves a point here at 1, 0. The moment we take that side and we start to open it up, right, the radius will never change. That length will always be 1, But the moment I do open it up, what starts to happen is this point will start to make its way closer and closer and closer to the y-axis, meaning this length will start to get smaller. So the bigger the angle I open in the first quadrant, the smaller the x value gets, because it goes from 1 down to 0, right? The opposite is true for the y values. As soon as I start to open up angles, the tip of my finger here at this point starts to go up, right? Which means that my y values are getting bigger and bigger and bigger. And so what you're going to see are x values at 3 of these spots, right? We've got 30, 45, and 60. The x value is going to get smaller. The y value is going to get bigger, okay? And if we had a nice relationship to figure that out, which we do, then we could actually write those coordinates down. Okay, and that's what I want to do, right? Imagine that we stopped. And again, remember, things are in motion, things are happening. We're just kind of like taking snapshots along the way as to what's happening. Imagine we opened ourselves up an angle, and that angle in there, call it theta, right, was 30 degrees. Well, we're good at this. Let's call it pi over 6, right? We open up that angle of pi over 6. And I just want to know where we are. We live on the edge of this circle. Imagine that it's us walking along, right? I care not so much about the area of the inside or the length of the radius, so that's not changing. I really just kind of care about where I am here. And when we're in 2 dimensions, I only have 2 spots that I care about. How far from here am I? And how far from here? Right, that's what coordinates are. It's a relationship to the origin, which is really us measuring an x distance and a y distance. I just want to know what that is right there and what that is right there. And because we centered ourselves at the origin, it makes it really easy to measure that distance. All I have to do is understand what shape I just drew. And what angle, let's go back to degrees because you might recognize that a little bit better, what central angle we're talking about, right? Central angle is ones that are coming out from the center of the circle. You drop a perpendicular straight down like that, you just made a right angle, right? And the relationships in right triangles are so much easier to deal with than any side angle relationships and things that aren't right triangles. So we lean on these as much as possible. Now I know that that leftover spot is 60 right there, but I'm not going to write in 60 because I don't want to get caught in thinking that that measurement is something I want to keep track of. The central angle is the only one that matters, right? Now what you might remember from geometry, or even a little bit from last year, is that 30, 60, 90 right triangles have side lengths that are in a nice, and I keep saying nice, I know, that are in a nice proportion. That if the short side is 1, so the shortest side is going to be across from the smallest angle, the longest side is going to be across from the largest angle, and the one in between will be in between. That if your short side is 1, your longest side is twice that. So if this was a 2, that'd be a 4. If this was a 6, that would be a 12, right? And that's one that we can count on every single time, no matter how big or how small this is. If it's a 30, 60, 90 right triangle, that proportion, and goodness, if anything counts in trig, it's proportions. That proportion can always hold. And to figure out what this side is, we have a lovely little a squared plus b squared equals c squared kind of setup. You don't have to do the Pythagorean theorem with me, but I just want you to see how nicely this works out. 1 plus b squared equals 4. Okay, subtract 1. Okay, so b, that side length that's missing, is just the square root of 3. Okay, and that every 30, 60, 90 right triangle, the sides are in this proportion. That from the small to the big, double it. And from the small to the medium, if you want to call it, multiply it by the square root of 3, right? So this was 1x, this would be 2x, this would be the root 3x, right? Whatever that would be. Okay? But we know what size our right triangle is in. What does this represent right here? What is that length back in here?
Radius.
And what's the length of the radius?
1.
It's the unit circle, right? So, but when I'm dealing with proportions, it's all about multiplying and dividing. I can't just add and subtract. I can only multiply and divide. So I need to take this, I gotta cut it in half. If I really wanna deal with the correct size, I need to cut that in half, which means I need to cut this in half and I need to cut that in half. And what that gives us, it gives me the x length directly underneath this point, which tells me the x coordinate at that spot, radical 3/2. And as not nice as that is, approximately 0.866, 0.866, it's perfect, and we can use it, okay? And same thing here, right, 1/2, and that's exactly 0.5, which is cool. Knowing that decimal approximation only really comes in handy when you jump into a calculator and you start saying like, you know, sine of 120 degrees, whatever, and it pops out some decimal. It can't change it to the fraction for you. It might be nice to know that the square root of 3/2 is approximately 0.866. Approximately. Okay. Just a nice one to have stuck in there. Okay. And even if I rotate, flip, turn, stretch, shrink, as long as I keep a 30, 60, 90 right triangle, these sides will always be in this proportion. And okay, then what if I opened up, you know, this angle, right? What if I opened up an angle that was 60 degrees? What if I opened up an angle that was pi/3 radians? Well, all that does, hopefully you can see me over here. Yeah, all that does is it gives me just a different, and I'm just going to exaggerate it so it's super obvious which is the short length and which is the long one. It gives me the same right triangle. It's just that my central angle is 60. And again, I'm not going to draw the 30 up here because I don't want you to think about that being an angle that we want to keep track of in the unit circle, because that's what it's all going to come back down to. But I do want you to know that we're in the same triangle. And if you're in the same triangle, the proportions are the same, the side lengths are all the same, that length is a 1. That's still the radius. And the side across from the 60 is still the same length as the side across from the 60. And the side across from the 30 is still going to be 1/2. And so this point up here has the same lengths to it. They're just going to be switched. Okay? And hopefully you know something pretty simple, that if 1 is less than 3, you don't have to write this down, but just think about it like this. If 1 is less than 3, then the square root of 1 is less than the square root of 3. And the square root of 1 divided by 2 is less than the square root of 3 divided by 2, right? And the square root of 1 is just 1. 1/2 is smaller than radical 3/2. And when I'm trying to figure out which one goes in which spot, when I open up an angle, I can imagine like dropping, so this perpendicular here, right, doesn't really exist except in my mind, but when I try to measure distances visually, to figure out, okay, where am I? I'm at a multiple of 30 or 60 and I'm in a quadrant, I know what my two numbers are gonna be. They're gonna be one of those, and I don't care what quadrant you're in, all of those are all going to have the same kind of coordinates because they're all going to be either 30 degrees away or 60 degrees away from the x-axis. They're all going to have those same two numbers, 1/2 and radical 3/2. And all I have to do is put them in the right order, where the x1 comes first and the y1 comes second. And I just have to pick in my mind, is the x length longer or is the y length longer? Is the y length shorter or is the x length shorter? Because I know that 1/2 and radical 3/2 are always going to come together. Any multiple of 30 or 60, because it comes from this right triangle, this special right triangle they call them because they're so nice. I know those two are going to come together. Okay. Cool. Hopefully this is mostly old stuff and you're like, okay, get on with it. Okay. How about the one in between? Out of space. Let's go this way. Come with me, desk. Let's go So here I am, 1, 0. Here's my first quadrant. Let's go halfway between. Drop that perpendicular straight down. Let's be in an isosceles right triangle. Okay, and the only way to draw an isosceles triangle is to have two sides that are the same. And if it's an isosceles right triangle, both of those angles have to be the leftover of 90, cut in half, 45 and 45. Okay, cool. The relationship between these sides are, of course, they're going to be the same. Okay, so your x length and your y length are going to be equal. Whatever they are, they're going to be the same. Now, I don't know if you remember what they are, so I'm just going to pick nice numbers. What if I picked 1? Okay, 1 squared plus 1 squared equals c squared. Okay, 1 plus 1 is 2, so I get the square root of 2. Okay, but that's not how long the radius is, right? This is where this idea comes from, okay? Well, I'm gonna pick something a little bit nicer, okay? What if I picked, so let's back it up a little bit, because dividing by the square root of 2 there is gonna make something kind of nasty and irrational. I'm gonna pick a nicer number. I'm gonna pick the irrational number as my length and my side. So square root of 2 times plus the square root of 2, both of them squared. Okay, so 2 plus 2. Okay, so that's 4. Square root of that is 2. That's better, because that's the one that we use, right? We had a nice length of 2 for that. So if both of my sides were square root of 2, yuck, gross, right? But square root of the square root of 2, 2. Square root of the 2 root of 2, 2. 2 plus 2 is 4. Okay, square root of that is 2, so that would give me a nice length, but that's still too big. That's 2 times too big. So let me cut that in half. Let me cut this in half. Let me cut this in half. Now, there's a million ways for me to get to this idea that if you're at 45 degrees, you're at radical 2 over 2. Okay, you would think that you would be at like 1/2, 1/2, right? If you were moving in a straight line, sure. If you went like that, if you cut straight across from 0 to 90 degrees in a straight line, sure, that spot right there would be 1/2, comma 1/2. But we're going along a circle, which takes us longer to get there. Right? Shortest distance between 2 points, a straight line. Okay? The square root of 2 over 2 is bigger than 1/2. It's actually about 0.707. Again, a nice decimal to have stuck up in your brain. Obviously, this is smaller than radical 3 over 2, which makes sense because I'm not quite as far, right? So there you go. And those are the only 3 numbers you need. Besides 1s and 0s, you need radical 2 over 2, which always comes in 2s. Look at that, there's so many 2s everywhere, you know, they come together because there's 2 of them. The 1/2 and the radical 3 over 2 will always come together as well, okay? Those will get you where you need to go. Okay, so what does that mean for us for the unit circle? And then hopefully, oh my goodness, time flies. I mean, I hope this class doesn't drag for you because it absolutely flies for me what I'm doing. Let's fill out each of these spots. Gosh, I don't know what it is about you guys. I talk more, I guess, in period 4. Okay, let's fill out these coordinates. What you're gonna see is that they're all the same based on how far you are from the x-axis. Because remember, I'm building right triangles. That's all I'm gonna do. I'm going to build triangles based on having the radius be my hypotenuse, okay? And so when I'm talking about, I'm going to give this thing a title here in a second. How far from the x-axis is your angle? I'm not necessarily talking about like going all the way to here and being 210 degrees. I mean, like this tiny little angle in there is only 30, right? That is what I'm talking about. Or like way over here at 315. I'm not talking about going all the way around. I want to build a nice right triangle using the x-axis, okay? That one would be 45 degrees because that's how far you are away, okay? That's called reference angles. Reference angles. R-E-F-E-R-E-N-C-E, reference angles, to refer back to one of those special right triangles. And what you'll see is that every single 30-degree setup, and I could say pi over 6, I'm going to say 30 to remind you, your coordinates will always be the same. I just have to watch my signs, positive versus negative. It's always going to be at radical 3 over 2, comma 1/2, at every single one. And what that allows me to do is to come to this. Let's go like, I'll stick with the green. I kind of like the green. Every angle that's 30 degrees above or below the x-axis have those same coordinates in the same order. Radical 3 over 2, 1/2 at 30 degrees. Same thing at 150, except the x is just negative because I'm to the left. Negative radical 3 over 2, comma 1/2. I'll even make that negative nice and red so you can see it. 210 degrees, same thing. Radical 3 over 2, 1/2. But because I'm below the x-axis, not only is the x negative because I'm to the left, but the y is negative as well. And same thing over here at 330 degrees. I'm 30 degrees away from the x-axis. My reference angle is 30 degrees, which means my coordinates are radical 3 over 2. If you are 30 degrees away, the first number you write has a 3 in it. 30 degrees, 3. Oh God, there's so many. I'm below the y-axis though, so my y is the only negative one. Okay, and you're going to see that's going to hold true for all of them. Okay, in the first quadrant, everything's positive. In the second quadrant, your x's will all be negative. In the third quadrant, both will be negative. And in the fourth quadrant, your y's will be negative because of where you are, right? There's 0. Okay? If you're at a multiple of 45 degrees, we're at that radical 2 over 2, radical 2 over 2, no matter what. No matter how far around the circle you've gone, really all I care about is a reference angle. An angle up or down from the x-axis that gets you a special right triangle of 45. Radical 2 over 2, radical 2 over 2, radical 2 over 2, radical 2 over 2. I can do it forever. Radical 2 over 2, radical 2 over 2. And look, I'm using that bar in the middle as my fraction. Radical 2 over 2, radical 2 over 2, just like I did with the radians. So all the way around 45, 135, 225, and 315. Anything that ends in a 5 is a multiple of 45. And look, they all have a denominator of 4. Yay. Last one. We got one last thing to show you. I'm going to leak a little past 11:15, so if you really have to go, you can go and just come back and see it. I just want to make sure I get to the same spot that I did with period 2. 60 degrees, same triangle as the 30. The order is just switched. Any angle that is a reference angle of 60. Anything that is 60 degrees away from the x-axis, going up or down to that spot, which is all the ones that are left, are all going to be 1/2 radical 3 over 2, 1/2 radical 3 over 2, there's 1/2 radical 3 over 2. All your negatives and positives in their correct spots. We'll come back to that at another date. So many. So I cannot, I would be here for 2 hours, seriously, if I told you about all the ways you can connect radians and degrees and coordinates all to one another, how, like coordinates to coordinates and radians to coordinates, and oh my goodness, there's so much. It blows my mind. You can see how busy this gets. Hopefully the colors help it stand out a little bit. But there's so much going on here that I don't really want you to sit there and memorize it. I really don't. But you just saw how I created it. You did it with me, right? That's how I do it. I don't have all of this stuff memorized. I mean, maybe by now, I mean, teaching it for 10 years, sure. But like I just visualize it. Oh, you want me to, like, sine of 150 degrees. Okay, like in my mind, boom, like I open and I'm closing my eyes because I'm using my mind's eye to see it. Like Okay, open up an angle of 150 degrees, and I'm still above the y-axis, so y is positive and x is negative because I'm over here. And like I have these thoughts that just kind of, I don't know, like start to appear in my mind. I don't know if like maybe it's just because I have more of like a photographic kind of memory, and visuals for me are so important in remembering. But I'm also very kinesthetic, right? I need to be able to, like I have to do things to be able to understand them, which is why I just did that with you. And if we were in class, you would have gotten like 4 or 5 copies of blank unit circles that I would, over a period of a couple of weeks, I would have you kind of recreate, and try to get an idea of how you're going to do it when the time comes. Okay, cool. Let me just talk one last thing. I know it's 11:15, so go if you have to, but start the video, 45, 50 minutes in when it's up, or go back to period 2. That one's already up. And just kind of pick it up right here where we start to talk about trigonometric proportions and what we can do with these x values, these y values, and really any size radius we want. We'll center it at the origin to make life easy. But I can create proportions, fractions, where I use 2 of these and try to build trigonometric functions. And it starts with proportions. Before we actually start getting into like f of thetas and h of thetas and g of alphas and t of betas and whatever we decide to use, we have to come up first with names for possible proportions. So what I'm going to do is I'm going to leave some space here. Okay, I'm going to put equals a fraction, down, equals a fraction, down, equals a fraction. I'm going to leave some space here. I'm going to do the same thing over here. Equals a fraction, equals a fraction, equals a fraction. And what I want you to do with our last couple minutes is I want you to, if you can, unmute yourself and come up with a fraction that uses 2 of these, and let's see how many we can make. Give me any pairing and tell me which one goes on top and which one goes on bottom. Don't use numbers. Just x's and y's and r's, and we're going to fill them in, and then I'll tell, and we'll give them some names. So unmute yourself, give me a proportion. Give me a fraction that uses an x, a y, and an r. So give me 2 of them.
R and y.
Okay, which one goes on top?
R.
Okay, r on top, y on bottom. I'm going to put that in the second column, middle. Give me another one.
X over r.
X over r. I'm going to put that one first, top left.
X over y.
X over y. That's going to go bottom right.
Y over x.
Nice. Okay, so because that one's the reciprocal, I'm just going to go straight across. I'll put that one over there. Bottom left.
Y over r.
Nice. Reciprocal, so I'll put that one over here.
R over x.
And that's the only one that's missing, right? If you've got 3 possibilities and only 2 spots to drop it in, and then reciprocals, there's only 6 choices, okay? And these 6 trig proportions, and for us, I mean, R is going to be 1 a lot of the time, which is awesome, but sometimes not, and it's okay. What they started to do was they recognized that no matter what, if you've got an x value, a y value, an r value, if you have an x length, a y length, and a hypotenuse in a right triangle, you can come up with proportions. And as you resize triangles, like if you were to take a picture on your phone, you zoom in and you zoom out, or if you take a screen grab of something and like you're on your laptop, you take the corner of that picture, instead of cropping it, you're not changing the proportions, you're just shrinking it, right? You can still tell it's the exact same picture, just a whole lot bigger and a whole lot smaller. What happens is that these proportions are all holding true. And when they decided, whoever they was, way back in the day, they were like, these are the only 6 we can do, and they all hold within the same triangle. No matter how big or how small, give me a central angle and it's a right triangle, these are all going to work. And they gave them all names, okay? The first one, so I'm way over here because I want to write something next to it, they called cosine. And they just took the first 3 letters of that, cosine, C-O-S, but they wanted it to be from a specific angle. So they wrote it with function notation, so they called it like cosine of theta, or alpha, or beta, or whatever Greek letter they decided to use. Cosine of some angle, they just named it. So like they created this language of trigonometry. The math was already there, but they created the language to talk about it, okay? The second one they called sine, S-I-N-E. And they just, again, took the first 3 letters of that just for brevity, okay? But it's of an angle, okay? The last one, you could probably guess, is tangent. Again, the first 3 letters, but they made it a function of an angle, okay? Tangent of theta. So I'm calling them trig proportions. I could really start calling them trigonometric functions, but they didn't really do that first. They started dealing with the proportions, okay? Then they came over here and they said, well, these are just all the reciprocals, okay? So you're looking first, like these over here are the 3 what are called basic trig ratios. Okay, these are the 3 reciprocal. I know I'm kind of probably up in the glare there, but I'm just writing the word reciprocal functions. But they named them the co-functions. Okay, and when we talk about co-functions, they relate across from one another. So you've got like this tangent over here. When I take the reciprocal of that, they just named it cotangent, so that they knew which one they were talking about, but that it was the reciprocal, okay? And so they, again, used the first 3 letters, C-O-T, right? But then they got to sine, and they're like, oh, let's just call that oh man, we already have a cosine. And their great idea of calling these co-functions really didn't last very long. Which is kind of a bummer. So you hear co-functions, I don't really talk about it as co-functions very often. I just call them reciprocal functions. But you're going to see something specific here, okay? Okay, here's what they did. They had to come up with another name. And that name was specific to more of the geometry that's happening in the background that I'll save you from a little bit. They called this first one, since this one already had a co in the name, they said, okay, well, let's drop the co. Let's come up with a word that starts with S. But let's pick something that means something geometrically, and it translated nicely to what a secant is in geometry. So they took the first 3 letters of that, and they call it secant, okay? My guess is that cosine, sine, and tangent are old news to you, but these 3 might be, okay? And look, this one has a co, this one doesn't. Good, so they are co-functions. This one already has a co, this one doesn't. So those are co-functions, they're just reciprocals, okay? Last one, cosine would be the co, well, we already have a cosine. So instead of calling it cosine again, they said, well, we have a secant already. Let's call this thing cosecant. And I like, it's just, that's why co-functions is such a lousy name for these, because they're hard to relate that way. But you'll see that each reciprocal, one has a co in the name, the other one doesn't, okay? But look, the first 3 letters, COS, no good, can't use that. So they picked the first 3 consonants, C-S-C. There we go. That's what I wanted to make sure I got to, okay? Your 3 basic trig ratios and your 3 reciprocal, okay? And now we can use them. Okay. We'll come back tomorrow to do that. Let's come back live tomorrow. Nothing you need to do for me tonight. You can practice unit circles until you're blue in the face, but I just want you to understand them one by one. But bring your unit circle with you tomorrow, because we're going to do some evaluating. Okay? See ya. It's 11:24. Get out of here. See you tomorrow. Same time, same place. Thanks, guys.
Thank you.
Thanks, Rosie.
Thank you.
If you have any questions, stick around. Otherwise, I see ya.